Hello, good afternoon. Hope you're having a good weekend. Um, Back on a more normal schedule today. Apologies for last weekend if you missed it. Had a pretty good session, and my friend Greg Bird was able to make it and talk about uh, lots of stuff that helped us figure out what we were going to do on HanoiDB and implementing it in Rust. Of course, he was involved in developing HanoiDB and also worked on BerkeleyDB back in the day. So, like, he has a long history of doing these low-level storage engines, and his perspective was helpful. Um, we have some interesting things we want to accomplish. Um, we got to the point of being able to read the the existing HanoiDB files. But we have a much bigger hill to climb to write them. And the with the design of the file format, it's not incredibly complicated. Um, I would say that the Berkeley DB is much more intricate in this respect. But what's I think interesting about HanoiDB is the tiered merging process. So if we can get to first of all, we should update our code probably to be able to load all the levels in a file. Now, obviously, we don't want to load the entire thing in a memory. So we'll probably want to do something like have a file open, um, and we seek that file to the position that we want, and then read from that. Uh, so so that'll require some changes on the read side. Um, but we could also do something like implement the nursery. So we could use like the built-in Rust B tree implementation, for example, to hold the nursery, and just implement the log. That might be a good thing to start for writing. And the next step after that would be when we fill up the nursery, then we promote the contents of that. So we write the contents of that out, and then we promote it into the first level. Um, and yeah, that would be even just getting the nursery um, would be really interesting. I think we probably want to think about our high level API. We're very much working at the low level of the file format right now. So we'll want to think about that. Um, and I was reading that this came up in reading the Reddit earlier this weekend. There's a We're not going to try to tackle this because it's very kind of specific to fully utilizing CPU. Um, but it's called the 1 billion row challenge. And on discussions of that, of a thread about that this weekend, I saw it reminded me of things we learned when we were at Bash Show. Is that actually people are concerned about compression, the cost of compression, but the I/O is going to be much slower than your CPU in general. So that's why things like Snappy and gzip are really great. LZ4, Z standard, all these things. They're really great because you are able to maximize your bandwidth to and from a longer term storage by making sure that what you store is as small as possible. And then when you need to read that thing, you can decompress it, and the cost of decompression is much less than the cost of shipping bits. I didn't quite finish it, but I was listening to the latest Oxide and Friends, which is a great podcast. It's kind of an open-ended discussion most times. But they last week they were talking to a fellow who has worked in developing silicon chips for a long time, and he was talking about the differences between chips. And one of the things that has been interesting since the end of Moore's law has been, what is the cost per bit? And by costing, the main thing is power there. If you're trying to reduce the cost per bit, and you know that the cost is high on I/O devices, which it typically is, versus going to some layer of cache or even the main memory, then you will want to optimize for the most efficient use of that power that's required to move those bits. And he was talking about things related to going from CPU to RAM and whatnot, and also the changing dimensions of how chips are built and like the packaging and whatnot. But I think the principle holds in a really relevant way for what we're working on. So we may look into adding compression as we go building the nursery. But I think now would be a good time to get started looking at where we were, since I've done my intro, and then we can maybe get to writing things into the nursery. So let's have a look. All right. Okay, so where we were last time, we have our main program. It expects, this is obviously just sort of a test thing. And what we might do later is move this into an example that you could run. For now, it's fine to just keep this as our way of exercising the contents of a HanoiDB database. So we take the directory to read as the first argument. It's our test.hanoidb directory. And then it's going to basically stat the directory. And readdir is actually enumerate the entries in there. So if it's not a directory, this will return a result of error variant. So next is on the iterator, we take the first entry, and then we expect to have at least one file in it. I don't remember what that extra unwrap was for. Oh, right. So this returns IO option of IO result. That I guess requires an additional IO. Okay. So we have to unwrap again, and then we get the path off of this dir entry. So that gives us a file to read from. Now that's not necessarily the way to go. When we're looking at this, there's this nursery.log. We could have opened that by accident. It just so happens that my file system likes us to open B10 first for whatever reason. So we'll need to get more specific about that. And then we read this tree from the file, and this is just loading the entire file into memory, which is probably not the right thing to do. We talked about that just a moment ago. And we should look into perhaps fixing that. What we'd like to get to is have a file handle in the tree and just read in the trailer, so that we have the bloom filter and the root block. And we, at some point when we get to actually writing these, we're going to have to ditch this data. I don't think that it's going to be reasonable or anything that we need to be concerned about with compatibility to be reading the bloom filter that was created on the Erlang side. We'll probably want to have a bloom filter that's native to Rust, that has its own serialization format. And then we can probably increment the version magic that we see at the beginning of the file. So like over here it says Han1 in this original diagram. We found in the code that it's HAN2. We could make HAN3, which would be the Rust version, at which point we can go, okay, we know that this bloom filter is not one of the bloom filters implemented on the Erlang side. And then we could also do other things, which would be like maybe we make, rather than using big endian numbers and having to flip bytes, we do little endian for the rest of these. That might be something that we could do for efficiency's sake with a new file magic. Okay, so in our example, we loaded the tree, we got the root block, expected it to have a root block. We inspected some things about the root block. We iterate over the entries in that root block, taking the first one. So we're expecting at least one entry in that block. And then in this case, we're kind of, we're doing fail fast type of stuff, with lots of unwraps and expects. In a real code, you wouldn't do this. But we're expecting that first entry is a poslen, so position and length entry, pointing to another block. So then we try to get the block from that entry, and then we loop over the entries in that child block. So yeah, that's what we're doing. This is kind of following the like traverse the B tree type of thing, but we're only going into the first one. Okay. So I think we need to learn some things. And let me just write out some things that we need to learn here. We need to learn what is the fan out of the B tree, right? Because we want to know how much should be in each block, in terms of keys or bytes or whatever it is. And then let's save, and we're going to save as to-do.txt. Okay. We also need to learn about the nursery, and the format of its data and its log. So suspect the log, the data is probably going to be exactly like the data in one of these levels, but you're not going to write the data file until the log. Well, I guess we can learn that. I'm making an assertion there that I don't know for certain. So let's not. And then we need to figure out how to load a tree without reading the whole thing. Without reading the entire file at once. Okay. Make sense? All right, let's look at format. At one point, Greg told me what this transact tag is for, but we're not using it right now, so we need to figure that out. Okay, so tree from file. I feel like what we should do is let's go ahead and make this more sophisticated. Um, and we're going to have to change a lot of stuff here, right? So the nice thing about this, pause len entry is that we can use these two things to seek to the right point in the file and read the exact amount. Now, the hard thing about the root block is it doesn't say what the length of the root block is. So we have to seek to the beginning of that block. Remember that the block length is the first 32-bit integer in the block. So it's interesting to me that the entries include a length, but the one at the end does not. So maybe we'll have to excuse me, maybe we'll have to deal with that. Right. So we'll need to change how block new operates, probably to make it either read the length, right, and then read that many bytes, or yeah, I think there's going to be some interesting things with the file handle. So if we look at I don't need to look at nom. Let's look at Rust. So if we have a file, we'll probably want to use buffered reads. But I think, let's see. What if this read, it's nightly. Read at, okay. Reads a number of bytes from the get offset. So we could potentially construct a vec to read into for each block. Okay, for our first pass, we'll probably want to do read exact at. Okay. See, there's seek read and seek write. Yeah. Okay, interesting. Offset is U64. So all of our stuff internally is usize. We probably need to convert them to U64s for offsets, because we were working on index into this, vector of bytes, which usize makes sense for that. But we probably want to use U64 for interacting with the file system. I wonder. Okay, so this is Windows only. I'm sorry. This read at. So we may even need to handle different operating systems here if we're going to use these methods that are in file ext. Note this is on WASI only. We got a lot of stuff there. So I think file implements read. Yeah, so we could do read exact. This is for sequential reads though. Okay. Yeah, that's nightly. Okay, the interesting thing there, note that like read is implemented for a borrowed file as well as for an owned file. That is really curious to me. That to me that says that you can read, like even internally move the file pointer, like the offset, the IO offset, without owning it. That's really interesting. Oh, and there's seek and okay. What is seek from? Okay. So you can seek from the start, end, or current. Okay. That's easy enough to understand. Again, it's implemented for borrowed files as well as for owned files. And right. So there must be. I mean, let's look at the Rust source. Why not? It's interesting that it jumps here. It's probably macros. Okay. IO traits arc. Okay, so let's see. Where's the borrowed file? So for a borrowed file, it goes self.inner.write. What is inner? I'm guessing it's like an RC arc or RC or something like that. Let's see. Maybe the inner is like they're abstracting over the operating system specific implementation. Um, oh, that's a good point. And a matrix, thank you. It's likely because the current seek pointer is stored in kernel side anyway, so it's a syscall. Oh, and I'm sorry, my camera's been all messed up here. Let's get that fixed. I accidentally opened OBS with the wrong resolution, and it moved all my stuff around. Okay, sorry about that, folks. That's an excellent point. So you don't have to have mutable access to the file handle in order to seek because it's a syscall. I wonder if the semantics on that are correct. It's obviously working for people, but that seems a little bit. Okay, let's. Where is the struct definition here? Let's just go back and source file. Okay. So yeah, it's got this internal implementation file, right, which is going to be operating system specific. That makes sense. So this inner, right, like they're just calling. This is a high level interface with zero cost over the base file pointer. So we could probably. I don't know if it's going to let me do it here, but if we looked at right, so sys fs as fs impl. Okay, so and that sys fs is okay, standard sys. Yeah, it's not going to be documented. We would have to dig through the Rust implementation, but okay. So we can. It's very very interesting. that we can seek and read and write without a mutable reference to the file. Okay, that means we could do some pretty crazy things. Nice things, I think, but crazy. Okay. Our block is going to have to be potentially changed. We might want to rewrite these as like read block, rename these. But okay, let's go back to the original problem. Let's make a new thing in here, which is file, fs file. Okay, and then let's, rather than having data here, this will be interesting too because it'll change our lifetimes. We're not borrowing from a shared buffer necessarily. It would be nice if the data, we don't really have like a sparse data structure with this, right? It'd be nice if the data were actually borrows. But what we don't necessarily want is to have to track which ones are read. So I think at some point what we'll do, maybe we'll just do it today, is rather than having the actual data here, have the block be initialized with, here's borrow the file, and have your own accounting of what you've read and what you haven't. And we could give you a start position and optionally a length. So for the length case, we could avoid some of the additional stuff that need to be done to like read the beginning of the length. So maybe what we do is we get rid of the data. This is going to cause all sorts of breakages, folks. Buckle in. And let's see, file. Let's look at that. So open. Right, so we were using read, which reads the whole contents. So opens a file. Okay, where's open options? Okay. And we just need read, right? Okay. So let's change it to that. Okay. So we're going to do, right, we'll change this to open options, new dot read true dot open. Okay. And this is going to be file. And then we need to, rather than looking directly at that, we need to specifically read. So file implements read. Let's go back to file, please. I suppose this is fine for read-only mode. Yeah, let's just do file open. Like that open options, we don't need those other things, so yeah, we can remove that. Okay. And then we can use read exact. Use vec macro. We want 4 bytes. And then we're going to do read exact mute magic. So that should read exactly 4 bytes. And then we'll say, if we say if magic borrow. Okay, so yeah, we need to declare that mutable. Okay, that's interesting. So there we go. So now we've read, there's going to be all sorts of other compiler errors. It's fine for now. So now we've read the magic from there. There might be some better way to initialize this, but 0 bytes is fine, I guess. And let's make sure, just for our own sanity, this is vec-u8. The compiler figured it out, but like for my sanity, I want that to be very clear. Okay, so now we've got a file in the tree rather than a data buffer. So we need to do a bunch of things. And I don't think that this is going to take that long, but we need to be, in each case, thinking really carefully about what we change. Now, I'm also, in this first, well, this is not the first pass. This is the second pass. First pass was read the entire thing. In this second pass, I don't want to be concerned yet with memory management. So even though we're moving to file operations, I don't want to be dealing with like making an arena that contains block buffers. Like that's silly at this point. Like we're so early in the process. The other thing that may or may not be obvious is that for one of the things we found when we were at Basho, that was just like a happy accident in a way, is that for the Bitcast storage engine, which I may have mentioned on a previous stream, it just stores the keys and their offsets into various files in memory. It does not do any other memory management. So it's not like it was keeping slices of files in memory and evicting them and like having cache and all that. No, it said, okay, the operating system cache is good enough. And it turned out that it actually was in most cases. So in this first pass at implementing Hanoi, or this second pass, since we were just reading before, if we're actually going to use file handles, what I'm not going to do is have a buffer pool, a cache, or anything like that. We can deal with that later if we need it for performance. So I'm not gonna worry about that. Okay, so interestingly, this may need to remain because we may need a borrowed file with a lifetime instead of borrowed data. That's interesting. Okay, so So let's, we need to do root block. Let's start with trailer since that's the most fundamental. We need to be able to read the trailer first so that we can get to any of the data. So let's see if we can modify this. Okay, we don't have this data thing anymore, but we do have the file, and the trailer is at the very end. So so we're going to have to change how we do all of this. Note that it does implement seek. So what we could do is seek. This is 8 bytes. This is 4 bytes. Okay, let's look at seek. What does the result mean? Returns the new position from the start of the stream. Okay. Okay, so let's go, and we're gonna have to import this. Okay. Seek from seek, right? So we're gonna need that. So if we go here and say self.file seek, that requires mute. Okay, we probably need to think about interior mutability here, or we just make all of these take mutable references, right? So that's kind of unfortunate, and we'll fix this one later. Okay, so we're going to seek from end. Takes an I64. Let's look at that. So sets the offset to the size of this object plus the specified number of bytes. Okay, so we do need negative value here, if I'm understanding it correctly. Okay, it's possible to seek beyond the end of the object, but it's an error to seek before byte 0. Okay, so we want to get 12 bytes back from the beginning. So I'm going to put here, root pause is 8, bloom len is 4. So we're going to seek from the end. And this is now we're going to have to start putting results on everything. right? Because now we need to start doing this. Whereas before we had the entire buffer and we only had a result on the constructor of this struct. So now we need to handle things as we're seeking in here. So we don't need that. So now we need to do we're going to allocate a vec to read into for these. And it's going to be 12 bytes, right? And then we want to do read exact. Okay. And then we can do, now we've got the, and this returns a result as well. Yeah. So we need to put question marks there. So now we need to we're going to do, instead of self.data, we're going to do buffer, and that's going to be 8 ... right? No, it's going to be 4 because there's only 12 bytes here and it's 8 bytes long. And then we read the bloom length is buffer, and that's 0 to 4. Okay. And now we need to get the, so this needs to be, bloom start needs to be an I64, right? Rather than, because that's what the contents of this seek from is. So we've got this. So let's say this is U64 and then subtract 12. The other way we could do it is add 12, right? And then we'll do we'll seek. The other thing that might be a problem here is this returns a U64, seek does, and we're ignoring it. We don't care. That, although the other thing is we could potentially go rather than doing this seek from end with bloom start, that needs to be I64. I hate those conversions like that. Make me a little nervous. Okay, and then we read bloom is going to be a vec of zeros, bloom len as usize, right? And then we will do I don't know if this code was there for dealing with the format here. That was coming from the Erlang side. There should be padding of 4 bytes, 40 bytes. right? At the beginning. Oh, before the beginning of the bloom filter. That's interesting. Okay. I'm a little concerned about, seek from the end. I don't. It's probably not going to be an issue because if we seek to the end and the operating system buffers, like 4K from the end of the file, then we're probably just seeking in memory. um, but like hinting to the operating system where you're going to read next is kind of an interesting problem to solve. Okay, so we're going to get the bloom filter, and then we also need to. Now, actually, here's the other thing that we can do. Rather than seek from end, um, we know. Let's say that's the current position when we've seeked to, but we're not. We're seeking and then reading. Yeah, we're seeking and then reading. So we're probably. Yeah, let me put that back. Let's do bloom start -4, because then we can check this trailer padding, and then we can read exact on the bloom size. And we're not really getting information about the file size right now. I think there's like a stat. Oh, interesting. Tell of nightly. Returns the current position within the file. Oh, okay. Well, we don't need that. What is this? Oh, that's interesting. Okay. As raw FD. Okay, if you need to get really low level. Um, okay, those are Windows only. We already looked at that. Now there's advise. Oh, that's nightly as well. Interesting. That's WASI. Okay, that's why it's nightly. Okay. Yeah, I'm not seeing exactly what I'm looking for here. What I was looking for is what is the entire length of the file. But we might, let's look at standard FS. Might have that from dir entry, like the metadata. File type is dir is file is symlink length, right? So we can get the size of the file in bytes. Is there on file? Yes, there is metadata. Okay, so I think it's worth reading that in the constructor. Um, and that way we can do some sanity checks. So let's do let len file dot metadata length. Oh, metadata question mark length. Okay. And then we can say length is in there. Then we can check that and here in the trailer and just go is the root self.len, and then we've solved that. So the root position shouldn't be outside the bounds of the file. Okay, so now we need to padding 0.4 and then let's do self.file.read exact mute padding, and we'll say if padding is not equal to that. Okay, and then we are at the position of the beginning of the Bloom filter, and then we will do self.file.read exact. What's interesting about this versus sorry, 1 second. Okay, so that's a U64, so we don't need to convert it to usize. Okay. And we need to update the trailer definition, right? Okay, so this no longer needs to be borrowed, no longer needs to have a lifetime on it. Because we're not going to, there's so little data here, we're not going to bother holding on to the file handle. And yeah, sorry, there's going to be some things I've done wrong here. Read exact is a result. Seek is a result. I need to make sure that all these places have question marks on them. Okay, so this can be a vec of U8 here. Okay. I don't know. Do we need that? Yeah, we don't. Okay. What's wrong here? Okay. Expected array. Okay, I guess I don't borrow. Fine, because the slice does the borrowing for me. Okay. What's wrong here? Okay, so this is where we changed this to result. So this needs to be okay of trailer. And then I think we've resolved everything in there. And there's no lifetime on trailer anymore. Cool. Okay. So here we need to do okay and question mark there, because I don't really like swallowing that result, but maybe for our first pass Actually, no, let's just return, um, because we're going to need to change block to use the file handle as well, right? Um, yeah. And we'll do a new method there probably. So let's do standard IO shoot result of block. We'll leave the lifetime on there. Hi, Chris. Good to see you. Thanks for coming. How goes the database? Well, we're trying to be a little bit more sophisticated. We're changing from using a fully read file into actually manipulating a file handle to read the things that we want. So encountering some challenges, but I think that they're going to be worth it in the end. Okay, so we've got the trailer. The first place that is used here is find the root block. So yeah, it's going to be exciting. So what we want to do here is let's assume there's a new method on this, and the thing is, this doesn't need to be a U size, right? This should be a U64 because that's what the file APIs expect, whereas the in-memory stuff is U size. So, minor distinction there on 64-bit architectures. They're the same type essentially, same memory layout, but they're for different purposes. And I think it's important to know that, like, the operating systems expect 64-bit. So, okay, so maybe, yeah. So let's say from start, right? And we're gonna pass the file. We're going to pass a borrowed file here. And because we can't just give the file to the block. We want it to be able to read the stuff itself and to be able to seek. And remember that we saw here that, surprisingly, read and write, and I don't know if seek was, and seek are implemented for borrowed files, right? Okay, so we should be able to do whatever we need to, like seek it, with a mutable borrow of an immutable borrow. Oh, my brain hurts. Okay, that is assuming I understand how that is written. So let's go down here and remember, we have all this stuff in block new, right? That expects an entire buffer. But what we would like to do is let's make a new one, which is from start, which takes a file, which is a borrowed file handle. I believe that's what we did up here. Yep. Okay. And the start position. And we'll have another one, or maybe we'll add an optional argument of length on here. Yeah. We'll probably need to add the optional argument of length when we have those poslin entries in the B tree that say, hey, the next lower level is at this position and length. That'll save us, having to read the length. Now, we may want to read the length anyway and validate just for integrity's purposes, but yeah. Okay, we're gonna have to change the struct itself, but let's start to look at how we would implement this. U64. And this should be again, I might want to make a type alias for this. And this is probably going to have to be TIC-A file, right? Because that's what we're borrowing. Okay, so here's the fun part. Okay, so if we say file dot seek, yeah, hey, look at that. Look at that. Seek from start. And this, was this a U64 up here? Start position is a, yep, U64. So yeah, that takes that, you can't seek before the beginning, so that variant does take a U64. Okay, so we're gonna seek to the beginning, and then we're gonna read so let's make a buffer. And how much do we need? We need, so there's a 32 byte or 32-bit block length, a 16-bit level, and then we compute the bound from that. I remember we did a lot of goop here. We can probably, rather than again, we won't, in this case, we won't want to read the entire thing, right? What we'll want to do is we'll change this up so that, yeah, we get the block length and the level, but we also should have the start position recorded. Pug. I don't know why I have pub on these. It's fine though. That way we can always seek the file. And let's just go ahead and get rid of this. File is going to be TIC-A file. And again, here, like, the point of having the file handle is not to be sharing memory per se, but it's so that if we want to go to, say, the beginning of the block and start iterating over its entries, then we can do that by a method on the block rather than having to go up to the tree and push everything up there. So, you know, since we're able to call seek on, you know, a reference to a file, then we should be able to implement this entries iterator by borrowing the file again and passing it, you know, like the start of the block and so forth. Okay. Okay, so we need 8 bytes, right? And then we're going to do file read exact, mute header. Okay. I'm trying to remember why we did 4 plus blocklen as usize here. That's okay. Let's copy these. And we're going to change that to header. Okay. So we have the block length and level. And here we need to, we're not going to read the entirety of the buffer. We're not trying to create a slice like we did in this version. So I don't know that we need to borrow with, or we need to bother with this. This was just about getting a slice of the correct length. You know, here it's length 0, obviously. Here this is where the data starts, so the key value entries start. We know it starts at byte 7 and it goes up to this. But what we can do is, in our new entry iterator, which will also borrow the file rather than the buffer, we can initialize it with, here's the start position and the length. And the start position will be, you know, this plus 7, because, you know, the compression is byte 6. I'm sorry, 0 indexed byte 6. Okay, so we don't need to do that. Is there a low level like read me 1 byte? I guess I could do read exact of, you know, a vector of 1 byte, but if an iterator for bytes, no, don't want that. The other thing that we could do here is, rather than 8, we can do 9, right? And then we can say let compression, because we know compression is going to come next. Is that right? No. Wait, what, did I do that wrong? Here, 7. Yeah, I knew I was off by something. Okay. So then we can say what we did before. Header 6 try into. Okay. We are not going to do okay because this is option, so we can remove these. The interesting thing here is maybe standard IO result is not sufficient, and I need to pull out this error. Hi, Isaac. Good to see you. Thanks for coming to the stream. I do want to, at some point, talk about the stream itself and like sort of meta about that today. But we can skip that. And, you know, there's one more thing that I'm going to do here. I think I need to start, like, doing something, because, like, this is trying to convert this slice into an array. And that's not going to fit in this type. I'll probably have to use our own. The other thing I can do here is go the problem is the error needs to be of the IO result type error. Yeah, let's just missing big announcement in the stream title. Yeah. Yeah, see, it doesn't like that because the error types don't match. I'm also not returning the correct thing. So here, let's just go forth and do this. Start, block len, level, compression, file. Okay. Now it's like these types don't match up. That's what I expected. So we need to make our own error type, which means I need to cargo add this error because I can't be bothered. Okay, and then we're going to and it's derive error, this error, right? And then we're going to say pub type result is going to be standard result of and this needs to be T, and our own local error. And here we're going to do something like we need to have an IO error, which is going to be standard IO error. We were kind of abusing that before with we were calling like this. We should make that our own. And this is it transparent? I'm gonna have to look up this error, see if I have it in here. I do. Cool. Okay, so right, we'll need to do that. This is from. Right, and we'll just do that because we don't care about the contents of it. Okay. And then let's start to figure out what these other things are. I actually like trying to put the wrapped ones at the bottom. So we'll have this invalid tree format. That should be one. Invalid tree format. And we can just have that as an empty variant. And maybe what we do is we put, let's put a vec-u8 in there, and that'll be the magic. And let's just go ahead and change this. Error, invalid tree format, magic. Okay, so if we get a file that doesn't have the correct 4 magic bytes at the beginning, we can throw that in this error and display what it is. Okay. Right, so I need to derive debug clone. Oh, standard IO error doesn't implement clone? Fine, we'll just do debug. That's interesting. Okay. So where is it complaining about that? Okay, so this is going to be our result rather than IO result, right? And maybe what we do here is, you know, we return, again, here it's going to be our result. So we might do corrupted file 0, and we could say corrupted file here, and we'll give a question about whether it's a string. Maybe we'll just do static stir for now. Stir. And we can here in trailer, rather than panicking. God, I didn't mean to create this entire error. Corrupted file. And here it's going to be missing trailer padding. And we'll do something similar here, except it's going to be root block position outside bounds of file. Okay. That's a little better. Fewer panics is good. And now we need to handle these. There's a question in my mind about what that error is. Obviously, it's not going to happen if we don't have a mistake in our code, and maybe it's okay to panic if we don't do that right. But let's see. We need slice. What I'm looking for is this. Where is it? Implements try into for a const size slice. I have to scroll or try from. Okay, let's see this. Right, so what we want, we're taking a borrowed slice and we want to return a borrowed array ref. Question is, what's the error there? Try from slice error. Okay. Standard array, try from slice error. That's what we want. Okay. Has a bunch of... Yep. I don't really... I really think it should panic. Buffer conversion error 0. Okay. So from slice error, and we'll say from, this is standard array, try from slice error. Okay, so now we can go down here. Where is it? Like this, try into, and we can put question mark on it. And the same here. It's interesting to me that this requires an array and not a slice, and it doesn't validate on that. Maybe because it's infallible. Yeah. Okay. Interesting. Let's see where else we have try into in this file. Okay, so here's where we were originally dealing with that, and now we need to make sure it's not standard IO result, but our local result type. And then where's our... We have the compression thing. Try from... Okay, and then maybe we just have a generic one. Right, because we need to be able to convert. Oh, this is a standard result. So complains about that. That is a really confusing error. Okay. Maybe what we do is here, rather than... Sorry, where did that compression thing go? The try from. Here it is. Okay, rather than this being static stir, maybe what we do is we just make this result our local result, and then we make a variant for this, and we just say invalid compression value. That's probably the better way to go. And this is error. We go invalid compression. Invalid compression. Let's just call it that. And maybe we let it have a U8 in there, right? And save value. Then we can print it out when we debug this error. Okay, so that's not good. Let's say error invalid compression type 0. And this is invalid compression U8. Okay. That's nicer. Seem to be jumping around a lot. Okay, so we've got this all converted into our new result type. We were down here in block doing this. So this returns the correct error type, so there's no conversion that's needed. And is that it? That might be it. In some ways that feels a lot better than this. We read the entire header in one go, all 7 bytes of it, and then we know what to do there. Okay, so we'll delete this. We no longer use new. We might make another version of this, like I mentioned, that has an optional length, and then we can compare it against the length we read. Okay, so now, right, so that returns result of a block. Now we need to go, like, this is wrong, this won't work. We need to go and fix potential. Maybe we should fix this. The other option here is we change this to result. Yeah, let's make a new. FN from start length, and we'll do basically this. Length is going to be, what was it in that entry? U32. That's interesting. Well, that's what's in there, right? So so let's do self from start. Let's say if let okay block. Maybe rather than that, we just go let block, and we do question mark, and then we will validate. So we'll say if block dot blocklen is length, then we return okay block, else we'll return, like corrupted file. That's kind of nice. Corrupted file takes a static stir. Invalid, mismatched block length given. This has to be a static stir. There might be a different way we could do that, where we could show, the block len and the length. How about we just make a different variant? Yeah, let's go to the definition on that. And this is what happens when you start creating your own error types. You're like, oh, let's make something that's really semantically nice, and then we can separate the formatting from the construction of it, and that's actually a good thing. So we're going to call this mismatched, or like incorrect block length, expected got that, right? Length, and we'll say, so this is U32 and U32. And then where were we doing that? We were down here. Okay, we'll say incorrect block length. And we'll say we expected length and we got block.block length. That's kind of nice. We don't need to mutate it here. Okay. So now we have this. Let's go. This is going to be we need this to be result, and we'll need to deal with this. Say return error. And let's make an empty variant here, which is going to be error expected pause len entry. Again, this is maybe something where we should panic because our code did something wrong. But for now, we'll do this, right? Okay, so now we can go from start length, and here we'll pass self.file and block position and block len. Okay. So we've got all the tree refactored to use file operations. We've got the block starting, initializing the block struct with file operations. Now we need to handle iterating over entries, and then we should be able to run our main program again and see that it still works. So we need to refactor entry, obviously. That'll be interesting. Haha, look at this to-do comment. Fun. So we will redo this completely, right? Perfect to do, right? I was telling my future self the correct thing. Okay. So we might want to do something like we'll have some error for this. We'll discover that as we go, I think. Or we could potentially use one of the variants that exists. Okay. So we need to figure out how much we want to read. Um, and this should return result, and we probably won't do usize. This will take, rather than buffer, it'll take file, right? The interesting thing here is we should be able to remove, because we're not concerned with borrowing from the file. We could do that. And then this will not have a lifetime on it, and these will be vec of U8. Right? I really, you know, my spidey senses is about about allocation are going off here, but it's probably correct. The nice thing about this too is if we, this is no longer copy, by the way. If we use vex, this means that the format we read in and the format we write in can be the same, which will be super nice down the road. Also, timestamps U32s, we should definitely change that to U64. Otherwise, we'll have problems in, what is it, 2038? Yeah. Okay, so let's change this to result self, because we're not tracking the pointer there. We'll just move the file head, right? When we read. Okay, so we can get rid of that lifetime. Yay. Okay, so now we need to do some stuff. Let's figure out the total amount we want to read. This check will be incorrect. We won't bother with that. Looking back at the design diagram, each entry again starts with the tag byte. It has a length, a CRC, and then what was the size of this? It's a 1 byte. So we know we need to read 10 bytes. So we can make a header. I'm just going to push all that stuff down and we'll move it around. It's going to be a vec of 9 bytes. Okay, and we'll do read exact on that. And then, depending on which one of these tags it is, we will allocate additional buffers. Although, yeah, because we know let me take a step back. We want to read the tag, and yeah, we need 9 bytes. And then we can allocate the entire length bytes to read the internal part of the entry. Okay. So let's make a header buffer. So we'll do file.read exact. We're going to be doing a lot of that. Okay, so now we have the first 9 bytes, which includes the tag byte. So we can do if header, and we need to start putting question marks on these things. If header 0, so let's just remove that. And we're not going to do this. What we'll do is we'll say return error. I'm going to say like corrupted file. And let's say first byte of entry wasn't tag end. So we're still using that, static string one. We could probably do something better. Okay, so now we're reading that, and that's header. We can remove the OK because we have a conversion error thing. Now here's where we don't, we're not going to bother with that because we were being passed a slice of the total file before, but we're not going to do that. So I'm not going to bother with this. You know, we'll just use read exact, and if it fails, it fails, right? And we just return that error, so it's fine. Okay. We don't need that because we're going to be reading sequentially, right? Okay, and we have the CRC. And here's one thing that I wanted to do that I've looked at since there's a better CRC library. Const CRC32 is not necessarily fast. I think that the actual one I was looking at was called CRC32 fast. And it uses SIMD if you have it, which is pretty nice. So yeah, let's while we're at it, let's switch to that. Let's get rid of that and do cargo add CRC32 fast. Okay. And then we'll do simple usage. We'll just do this. And we'll need to deal with this. Okay, so that's wrong. We'll fix that. Okay, so this is header. Okay, so now we can't compute the CRC32 yet, right? What we can do though is we have the length here, which does not include the original CRC32. We can what am I trying to say? We can read that many bytes. So let's say let mute entry is going to be a vec of zeros of size length as usize, right? Okay. And that needs a bang. Okay, and then we're going to do file read exact mute entry. Okay, note two that length does not include the tag byte for the next entry or at the end of the file. The end of the block is probably the proper way to say that. Okay, so now what we can do is we can just say entry. Okay, and then here we'll do this doesn't work for because we were formatting there. Let's for now we'll just not care about what the values are. That'll only be relevant if this algorithm produces, which it shouldn't, produces an incorrect CRC32 based on the understanding of other implementations of CRC32. So I honestly don't think that it's going to be entry had incorrect CRC32. We'll do that for now. Okay. All right. So Um, let's go down here. Okay, so here what we're going to do, let's not rename that. Let's just call that entry data. Because we're going to return something different down here. So this is entry data. I didn't want to have that like be confusing as to what it's shadowing. Okay, so entry data. Now the other thing here is this is entry data 0. We're gonna have to recompute all of these offsets because our header, right? I missed a question mark on line 204. Thank you very much for pointing that out, Isaac. Yeah, cool. Thank you. So we're doing a bunch of changes here. There. This is going to be 1 to 5. So if it's a key value entry, right? There's key length there. And that's not 14. That's going to be boo. I'd have to relitigate all of these slices. Oh. Okay, and then the value is going to be just the remainder of that. And this is not buffer, this is, entry data, right? This is entry data. Now, the other thing we could do here, because these were originally slices, what we need to do is, I think that Vec has a split off method. Something like that. Yeah, split off. So this returns, okay, splits the collection in two at the given index, returns a new vector containing the elements from at to the end. The original vector will be left containing the elements 0. Okay, so want to take ownership of an arbitrary subslice, or you don't necessarily want to store the removed items in a vector C vec drain. So we need to think about this. The other thing we could do here is go to vec and just copy for now. Because what I would like is potentially, we've already allocated this vector. The key and value need to be vec u8s, right? So maybe we can see, maybe we can do 2 split offs rather than this 2 vec. And that takes me itself. So yeah, let's do entry data. And we don't okay, so we'll still need this, right? I think. No, because okay, so this is going to mutate entry data. care about that because we're going to split it. So we'll say entry data dot split off at starting at byte 5. This takes return, what it returns is a new vec that starts at that byte. And then we can do key split off keylen as usize. Yeah, that's nicer. Okay, Isaac says, recently I had to work with some old protocol and the CRC implementation was a mess. Wireshark plugin had the option to switch between CRC implementations, and I found some bugs in the Python package I was using. You're lucky. CRC 32 is pretty common. Yeah, it is so common. Yeah. Okay, so that actually, I feel like it reads a lot better. Right, so it starts at and then goes up to the length, exclusive, and then the original vector is left with this. Okay. Yeah, and then we'll do the same down here for these things. So in the timestamped thing, we're going to do, again, this is expecting 9, so this is going to be 1 to 5 again. 1 to 5. And the keylen is going to be 5 to 9. And then we don't need the key upper bound thing again. We're just going to do let mute key is going to be, and this is not buffer, but entry data. So here we're going to do entry data split off, and we'll start at 9, right? And then the value data is going to be key dot split off of keylen as usize. Okay. And we can remove these OKs because we handled that particular error now. We're getting there. We're getting there, folks. And then we can change the entry iterator after we're done with this this change. Okay, again, we're going from 1 to 5 here. We'll remove the OKs, and then we don't need that. And then key is going to be this is entry data. Interestingly, like in that format, then for this, the key length is almost pointless because it's a deleted entry. You just need the length. Potential optimizations I suppose there's some consistency there of having, if it's a key value or deleted, that the next 4 bytes is going to be the length of the key. Even though that's subsumed by this length. And it's really only valid or important for like where's the split between the key and the value here. Interestingly, on the position length one, with the starting key of that page, of that block, they don't care, right? There's no keylen in there. Interesting. Okay. Okay, so here we can go entry data dot split off at byte 5. Okay. And then let's go forth and fix these. This is basically this. We don't need mute there. And then this will be very similar to these others. So 1, and this is 8 bytes, so we need 1 to 9. And And we need 9 to 13 here. And the key, and look at all that goop that we can get rid of. Entry data dot split off at byte 13. Entry data. Okay, and then here, you know, we can do. We might want to consider. This is going to be okay of entry. We might want to consider doing a new error type here. We might be able to look at some of the other errors that we're returning. Let's just make a new one for this. Let's say invalid. Invalid entry tag, and that's a U8. Okay, and here we can go return error invalid entry tag tag. Okay. Now, let the fun begin. We need to be able to construct this entry iterator. And remember last time that when we implemented this, so first of all, I don't know if that is necessary, that lifetime. We'll find out. I suppose it is because you're borrowing the file. Here, let's change it to borrowing a file. But the entries are no longer bound by that lifetime. Okay, so we're going to need more stuff here. We need to know when we've reached the end of a block. So we probably need to track the start, end. And then rather than this, because this was about slicing buffers, what we can do is we can say if start is greater than or equal to end, return none. And then we'll do our accounting of where we are. So maybe this needs to still return result of self usize. So we're going to need to maybe just make a value here and go amount read. Does this return? We can probably start that with 9 and just note that that's length of header. Start with length of header. And honestly, actually, we can probably do, rather than accounting for it step by step, we know that it's going to be 9 bytes plus the length that we read here. And then if we get through all of this, we can go 9 plus length as usize. Except the thing is that needs to be U64, right? Um, interesting. I wonder if there's like a converse trait of read. Because remember, read is about like sequentially reading bytes from a file or from a stream of some sort. Um, okay, we're going to delete that. Um, and here we'll go self.start. And let's rename that red amount. Okay, what's wrong here? Oh, self.start, self.end. Okay, so this returns a result, so we have to do .ok on it. The other option is to go do something with that value. I don't know if in the middle of this iterator is the right place to do like log something. Add an event to a trace. I'm not sure. I want to say there was something with fallible iterators, like try next or something like that. But it's been a while since I looked at that. The other option is that we do, rather than option, or rather than this, maybe what we do is result of entry. The problem is that if we get error clause, then we need to make sure that the iterator doesn't do anything. Because if there's any reason why this failed, then we shouldn't continue iterating because the file is corrupt, or there's some other problem that's internal to this implementation. Okay. Interestingly, the other thing that we could do, rather than returning that as the computed, we could have entry compute how much space it needs. That might be useful for the writing side as well, because we'll need to allocate, right? That might be a fun. Excuse me. That might be a fun exercise. Okay. I'm okay with this sort of swallowing the error for now. We might want to rethink this. The other thing that's interesting about this is we might need to do let's go ahead and do that here. That way the entry starts at where it expects to start. And we don't have to make the assumption before we enter that read me an entry method that the file hasn't moved, right? The other thing we could do is we could put that into entry read. Then it would be generic if we wanted to jump to any particular part of the file. We could, I suppose that's not that necessary right now. Let's just go with this. I think having this seek right here, except it needs okay. If you can't seek there, then there's nothing there. Yep. Okay. Is there anything more? Oh, interesting. See that? It found that the compiler found the thing that we decided we didn't care about. On those deleted entries, you don't need the keylen because you have the length of the entire entry. Interesting. Okay. I suppose in the original code there was probably a reason why that exists. Like probably like layered levels of encoding, where if you have the key, you put the keylen and then the key. So TLV type format is what this is. Okay, so now from here, we need to construct this entry iterator correctly. So it needs a file. So it needs self.file. What else does it need? It needs the start. So that's right, self.start. Except it's not self.start because we have to go. We've got these header bytes on the block, so that we've got 7. Okay. And then it needs the end. Will be block length -1 plus start, because we got to have a tag byte on the end of the block. I'm sorry, it's give me a second, Isaac. It blurred out some of something desync because increment is skipped by early return on error. Yeah, possibly. I think the contract is, obviously your iterator should always return none. And maybe what we do is put this into a state where it will always return none on subsequent asks, but the for loop and like all the iterator methods will stop on the first none. So yeah, we'll need to make sure that we protect that invariant, or we're a little defensive on that. So maybe we need some if-lets in here instead of just .ok. Let's come back to that for a second. I want to finish constructing it correctly. So the end will be self.start plus self.blocklen as U64 -1. Okay. So we'll say block at entries always end in tag end. right? Skip the header part of the block, 7 bytes. Okay. Self.start. Okay, that's what it was blinking at. Won't self.start desync because increment is skipped by early return on error. Yeah. So let's go in here and say if let not if let. Let's do let okay. We'll do this. Okay, so if you can't seek, we'll say else self.start equals self.end, right? And this will make sure that we've terminated. So if you can't seek there, the other thing that we could do potentially is here, let me back that out because I think that there might be a better way. We can do something like map none on option. It's not map none. Not or else. Yeah, we'll turn this into a match. I think we'll do we'll say if this is error, then self.start is self.end. And we'll say ensure iterator terminates when there's an IO problem. And we'll just have these cases of like what is our, and this will give us an opportunity too here if there's for maybe to say if let error and then ignore the value, and we can come back later and go, what is that? Do we care about logging it or something? Yeah, and then, but it's the and then is always a positive. We want to check if it's the error case. So let's do something here. Match entry read. We'll get rid of the OK. And if it's some of this, then, and this is maybe a case where we could do a map. But for now, let's do this, and then error, whatever. Just return none. Yeah, there's probably a bit more functional way to do that. Some entry. And we can get rid of that. And we can do the same thing here in this. And there's a problem reading an entry. Okay. That feels a little bit clearer. The interesting thing here, though, is if we have advanced this, the file handle, and we're not doing anything else with the file handle in the middle of the iterator, this will already be at that position. It'll be almost a no op. That's actually not a bad thing. Okay, let's see what other errors. Yeah, I used the fully qualified. What's going on here? 0 lifetime parameters. Where is it expecting a lifetime? Oh, here. Jump to that position, please. Okay, so this takes an entry. And here, I actually think I want to change it to a borrowed entry. Because you can't, last time I think we had it be copy because there's just references inside it. But here it's, it could actually contain data that are allocated, and we don't want to consume it necessarily. So we'll have to figure out where that's called and fix that. Luckily, this, go there. Okay, and we'll borrow that here. What else? Cannot mutate immutable value. Oh, right. Okay, so now we've got this has to take mute. Or does it? Can we get around that? Let me see. You know, I don't think it needs to be. Can we change that back to borrow? Can this be borrowed? Okay, so here, right, okay. What we could do is do let file, self, let mute file, self.file. And then this struct doesn't have to be mutable because we can mutate a reference. Let's see. All right. Variant name ends with the enum name. Clippy. Slice conversion. There. What else do you want me to fix? Clippy. Unused standard result that must be used. Okay, so there's a case where we need to do question mark. Use the left value directly, magic. Okay. Okay. But this is intention, yeah, okay. Those are never used. That's fine for now. We will use them eventually. And in fact, what we might do eventually is not read that, but actually construct the bloom filter. We're just not doing that right now. Okay, there's another one where we didn't use the result. Probably more of those. Oh, okay. Yeah, self.file is already a reference. Yeah. I think okay. We'll make Clippy happy here, and I'll put a to do. Let's say to do check the result of the error, or maybe like don't swallow the result of the error, or the result of the above call. Yeah. Isn't the cursor a property of the file, or has the rest standard lib some extra state to track the offset of each individual handle? Pretty sure this wouldn't work in C. Yeah, actually, before you joined, Isaac, I think Enigmatrix was saying that that is actually tracked by the kernel, and that so that's why it's. Oops, I didn't mean to pop that open. That's why you can have a mutable thing, which is a reference to the file, and the y file implements read and write and seek for references to the file. So it's that the operating system owns that struct, and you're actually just borrowing it, even when you have an owned file. Because it ends up becoming syscalls anyway, with like whatever the file descriptor the operating system gives you. That's just a reference into its data structures. So you're not actually mutating anything in the user space program. I think the reason why these are mute is because for some kinds of things, like for example, read is implemented for slices, and so let's see, where's you should be able to link to who implements this. But for things where the you can implement read, write, seek, etc. for things in the in user space. So it does a dupe under the covers. No, it doesn't dupe under the covers. It's just the how to put it. The mutation of the state happens in the operating system kernel, not in user space. But for other purposes, read has to take a mutable reference to self. So it's safe for some definition of safe for read to be implemented on references to files. Okay, let's see here. What's going on here? Oh, right, because this is okay. So now we've just got concerns about deep, dead code. That's pretty good. Let's see if our program still works. And then we should wrap up for the day. Okay, so we panicked. We have some things to fix. Interestingly, we did get the root block. It did find no compression, length 978, level 1. It read the first entry. So let's look at line 25. Yeah, do experiment with that one. That was actually, we just discovered that today. It's surprising that, I mean, it makes sense, I think, from the perspective of how do we actually interact with file systems. But yeah, let's look at what's going on here. So line 25 of main. Okay, so I think we've actually tackled this. Let's just say, let's turn this into a markdown file probably. We loaded a tree without reading the entire file at once, right? We're gonna get there. Answer these other questions next time, perhaps. Okay, so we got the root block. Um, could not find child block. Where does that happen? Incorrect block length. So it expected 8736. We got 8732. That's what our error up here says. So expected 8730. So it's off by 4. That's interesting. Um, so I think what we have here is that this is an off by 4 because the block length is 4 bytes. So I think what we need here is let's say let expected length minus 4. That way yeah, because this is the length is the total length of the block, including the 4 bytes that it takes to read the block length. Let's look at the diagram. Make sure I'm not completely off here. Yes. So this is block len. This is the entire length of the block. Okay. If you weren't confused enough already, let's move forward. Okay. Okay. So we were able to iterate over the keys and values in that first page. So we've got the root block. We got the first entry. It starts with, the key 9797 and value 9797 and so forth. And then there's just, I think those are A's. And then we get to B's and so forth. So we were able to convert. Our iterator works. I think this is a pretty good place to stop for the day, even though we're over by about 20 minutes. So I'm going to make a commit. We're going to do... let's rename that. Rename. Okay, that's a markdown file now. Okay. Okay, this is session 3. Rework reading file, rework tree to read from file handles instead of loading the whole thing. This will become more relevant when we're trying to do stuff like search for a particular key in the entire database. Because remember, a tree represents only one file. So that'll be interesting place to pick up next week. And we can do, we can start looking at the nursery in the Erlang side. And maybe we can start to implement the nursery so we can get the first version of rights. That'll be super interesting, and we can we'll have to figure out the fan out of the B tree at that point. Yeah. Okay, so I promised a little bit of meta. I've been toying with the idea of streaming on YouTube instead of Twitch. I would love to hear your opinions. Send them to me now in the chat if you're still here, or if you are watching this on YouTube later or on Twitch. Please send me a comment, either on the video or to one of my socials. I'll probably also post this question on like as a reply to all of my announcements that I do every week. So I don't think it'll happen next week. I want to give it some time to collect results. I was inspired by Chris Biscardi. I don't know if you're still here, Chris, but he does his streams on YouTube. He puts up the announcement, shows up in people's feed. Yeah. Oh, hi, Chris. Glad you stayed on until the end. Um, so like I'm considering that there's extra work for me to, record locally and stream at the same time. And yeah, I know you're obviously pro YouTube. There's some nice things about it. So I am considering that. If you have strong opinions, please let me know. If you don't care, I'll probably still do the same thing. I'll post that the stream's coming. I will, you know, I'll schedule it on YouTube. Yeah, Isaac. Okay, so you don't care. um, I'll schedule it on YouTube. I'll post notices on all the social media sites I'm on, and then you can come as you are. So if you don't have a strong opinion, then we'll probably move to YouTube pretty soon. I feel like it's been growing in terms of visibility. My stuff is showing up in searches. There's no like limit on the lifetime of VODs. So I don't see a reason not to move over there right now. Twitch is largely for gamers in a lot of ways. So like programming content doesn't bubble up as easily as it would on YouTube. All right. Well, with that, I hope you all have a lovely Sunday, and I will see you next week, hopefully. Thanks.